Good afternoon, everybody. Let's go ahead and get started for this afternoon. Today we have a homegrown speaker, Dave Montgomery, one of our geomorphologists. Just a quick background, Dave got his bachelor's from Stanford, then went to Cal Berkeley, where he got his PhD, studying surface processes, and has been with us, since
Since the late Pleistocene.
Yeah, 90s, I think.
Early Pleistocene, thank you, yeah.
Dave, as you know, has been focusing on science communication, and he's published several books, which hopefully some of you have read. And today, Dave's going to give us a potpourri, excerpts from maybe 4 books.
Yeah, at least.
And maybe some future things he's thinking about, because I know he's working on a new book currently. So hopefully we'll get enlightened further. And his books covers a whole range of topics, which we're going to hear about, everything from soils to floods to salmon to agriculture to health. So quite wide-ranging. So take it away.
Well, thanks, David. And first, for those of you who are over 21 or have a fake ID, come on out to any of these shows. I play in a band. We're pretty busy these days. If you like the kind of stuff that we do, check it out. And so I'm just advertising the availability. The Sunset is a great bar over in Ballard. In terms of other stuff, I'm going to be teaching a seminar for the first time in ESS this spring on books that I've written. It focuses both on the content and the process and acts of science writing. Anyone who's interested in how you reach a broader audience than the wonderful world of our peers, you might think about engaging in that seminar or discussion. We're going to look at an environmental history of salmon, an environmental history of farming, and the relationship between science and religion. And no, I am not a creationist, but I have written a book that deals with the origin of the world's flood stories. And just as a big hint, it was longer ago than 6,000 years. That's not what I'm talking about today. What I want to talk about today is literally the most recent book that my wife and I have written. It's called What Your Food Ate. But what I want to do is tell you the story, really, about how a geomorphologist would get interested in writing about human health, and I'm now publishing in medical journals more than in neuroscience journals. That's only been in the last year or two. But it was as much of a surprise to me as it might be to some of you. And I'm going to tell you basically the intellectual story of how I kind of got there from the world of thinking about soil erosion to thinking about what our food ate, which is the subject of the most recent book. But first what I want to do is basically give you guys a quiz. And I guess I control. You guys mind if I turn the lights to half off? Where is the room controls? I'm just going to assume nobody wants to take notes, so I'll avoid the note thing. But the quiz is, which planet would you rather live on? Team blue. Team red. Only a few people ever vote for Team red. Why is that? Well, because they're more adventurous than the rest of us, I think. But what is it about Earth that makes it special? We all know, just from looking at pictures, that they're different colors. The blue is free water, no big mystery there. The white, it's an atmosphere, there's clouds. But the part that often gets left off in thinking about planetary habitability is the soil. This little bit of brown stuff that pokes through on that. We can argue about whether or not there's soil on Mars. There's not. It's regolith. But there's no life. What's so special about this planet is the mix of biology and geology that really comes together in the soil to make the planet fertile and support the growth of further life. And so I kind of got sucked into thinking about the formation and nature of soils and how that really has played out over time in writing Dirt, the Erosion of Civilizations, the first of those books that I just showed you. And it's one where I initially thought I was writing an environmental history of soil erosion. Why? Because as a geomorphologist, I study soil erosion. I've worked on how erosion shapes mountains, hills, and so on. And it turns out that in writing a history of soil erosion, what I realized in the end is I was actually writing a history of farming. Because it's the act of farming, the way people interact with the environment through how we raise our food, that has actually really shaped the history of soil erosion in the Holocene for the most part. And you can summarize the 3 main takeaways with this book is that societies that don't take care of their soil don't tend to last. I think that's one of the most underappreciated lessons of the last 10,000 years, especially when you map that into what our current policies are in relation to the soil and sustaining its sustainability. There's a clear message in the archaeological and pedological, the soil science record, that you can put together. And soil erosion and degradation have limited the lifespan of past societies. That's a conclusion I came to in writing this book. It doesn't apply to every society, and I'm not arguing that soil erosion killed off everybody in ancient Rome. But the way people treated the land set the stage upon which their descendants were able to support themselves or not. Turns out if you have a small population and a lot of fertile land, you can grow. If you have a large population and you are running out of fertile land or degrading your land, you shrink. It's fairly simple and fairly unappreciated. That's the story I put together in Dirt. But I just want to point out that soil erosion that could actually threaten a regional or even a global society is not actually just ancient history. It has played out in history in the past, but it's something that is very current today. This is the UN's global map of soil degradation it's about 15 years ago, and it's painting with an incredibly broad brush. Don't believe the details on this map. But look at the pattern of red on it. You can kind of believe that. Areas of the world with very degraded soils. The island of Madagascar, if you've ever opened a book on soil or global soil erosion, there's going to be pictures of Madagascar in it, guaranteed. You look at the American Midwest. This is where Isaac Larson, the guy we were interviewing a few years ago, has done very recent work confirming that a third of the topsoil from that red thing is basically gone in just 100, 150 years of farming. The global estimates of the magnitude of land that's been taken out of agricultural production because of soil erosion during our agricultural history varies from about 25% to about a third in terms of credible estimates. That's a lot of land. It coincides a lot with those red areas. You can ignore the orange areas. I mean, I don't think the Amazon's that degraded yet, right? Pieces of it are. But if you look at the most recent global projection of trends in soil erosion and soil degradation from the UN's Global State of the Soil Assessment in 2015, we're on track to lose about a third of a percent of our global agricultural capacity, our food production capacity, each and every year to ongoing soil erosion and soil degradation. That 0.3% a year is cumulative. So by the year 2100, we're on track to degrade another third with business as usual. If our population is going to rise by 50% in that time frame, it makes no sense in terms of planetary management to lose a third of our agricultural production capacity. This is why I got sucked down the rabbit hole of thinking about soil and soil integrity, and as we'll get to, soil health and how it maps onto human health, not just at a societal level, but on each of our individual levels in terms of what's in what we eat. So in that Dirt book, there's a villain. That villain is the plow. How many of you have ever thought of the plow as a villain in a book before? One of you, all right, a couple of you are way ahead of the global curve. But that was the conclusion I came away with in writing Dirt, was that it was the systematic act of repeatedly disturbing the soil with physical implements, turning it upside down the way tillage does, that influenced soil erosion in ways that could help undermine civilizations. Now, why is that? Well, what does a plow do? It turns the soil over. What does that leave it as? Bare and vulnerable to erosion by wind or rain. How many places in the world that you guys have done field work in, and I know a lot of you have worked in a lot of places, how many natural landscapes do you see where vegetation does not cover the earth? Nature tends to clothe herself in plants, other than in the Arctic, so, glaciologists, you didn't need to raise your hand, or in like real desert environments. But the real productive ecosystems of the world are all shrouded in soil, and plants. The coevolution of soils and plants goes back some 450 million years as well. But anyway, what I concluded in Dirt is that soil erosion and degradation played a role in the demise of ancient civilization after ancient civilization. A number of them are listed up here where there's very solid archaeological and cultural evidence and that you can piece together with the current state of soils to basically document that. That's what I did in essentially writing Dirt. And part of the fun was not just looking back at what happened to Rome or classical Greece, where the story is actually pretty clear, but looking at the history of the United States. In a region of the country where some of my own ancestors left in the 19th century, probably because of land degradation, although that's kind of lost to the clouds of time. This shows you the magnitude of historical soil erosion as reconstructed by Bob Mead and folks at the USGS back a few decades ago. That gray noodle covers the Piedmont or hill country of the Appalachians. So that's not the coastal plain, not the spine of the Appalachians. This is the upland hill country. Notice that that gray noodle represents 4 to 10 inches or more with the black of topsoil that's missing as a result of just a couple centuries of farming. It's worth noting that if you go back and you read the journals of some of the early plantation owners in this region, they described 6 to 12 inches of thick black earth over red subsoil. We've lost a half to all of the topsoil across an area that was one of the breadbaskets of the early North American colonies, and we've done it in just a couple centuries. Now, after I wrote this book, Paul Bierman and some of his grad students basically used cosmogenic isotopes to basically confirm the pace of this story, that post-colonial agricultural erosion was 10 to 100 times faster than the background rates. Very similar to what Isaac's been documenting in the Corn Belt across the American Midwest. But that's not just limited to the East Coast or the Midwest. This shows you a slide from eastern Washington, from the Palouse. It's taken back in 1970. It's a winter wheat field. You'll notice the absence of winter wheat. This is what happens when you plow a slope on a hillside and then it rains. All those little channels are things that a geomorphologist would call a rill. You can erase them with a single pass of the plow. You can keep farming this land, but where does that soil go? Well, downhill. The estimates of the magnitude of soil loss from the Palouse as a result of this kind of activity happening year after year at this point are roughly 50%. What does that look like in some places? Well, this is a fence line that Vern Kaiser photographed back when I was born in the Palouse. This is not all terribly new news. We'll get to the newer stuff in a bit. But this is a fence line at the edge of a field that had been plowed regularly from 1911 when it was first farmed to 1961. At that time, this cliff had developed. The farmer didn't want to plow over the fence around his water cistern. How much erosion of this in 50 years? That little black thing there is a 1 foot increment on a survey rod that's kind of washed out on the negative. That's a foot of erosion in 50 years. That's about an inch a year. There's nowhere on Earth that soils form at that fast. The closest rate is one that Isaac and I documented in New Zealand years ago, pushing a millimeter or so a year. If you're losing something faster than nature can replace it, you're running out of it. The question is, how long will it take and how fast is it going? This is all to put kind of a perspective on looking at that historical analysis of prior civilizations. If we could do the same thing to the Palouse and the Piedmont that the Greeks and the Romans and the Mayans and the Chinese and I could go on and on in terms of listing cultures that have compromised themselves this way, but it puts into perspective that it's not an insane argument to make. This shows you a difference from contemporary coffee country down in Costa Rica. 2 slides of on the same hillside, one of which is in a forest preserve. And these are road cuts, right? Geologists always take advantage of road cuts. This one is in a forest preserve. You notice my notebook there is about a foot of black earth over the reddish subsoil. On the coffee plantation, there's no topsoil anymore, less than 100 years. They now have incredible disease problems with their crops in the areas where the topsoil has been missing. And the reason why will hopefully become clear as I talk about the second book that we get into. Now, one of the things that I did in writing Dirt was, as an academic geomorphologist, it was a lot of fun to go in and look at the archaeological record, look at the soil science record, and so forth. But I wanted to know whether or not the rates of soil erosion that you might actually get off of plowed fields were enough to explain the observations of loss of soil from past societies. So I went to the library and compiled every bit of information I could on how fast the world's farms are eroding and how fast the world's natural landscapes are eroding. Compiled something of 1,400 different studies, and what I came up with was that modern agriculture erodes off an inch of topsoil in about 20 years. That's a millimeter a year, basically. That's kind of slow. Your fingernails grow faster than that, right? I mean, only a room full of geologists could get excited about something happening at a millimeter a year. But when it takes nature 500 to 1,000 years to replace that inch of topsoil, alarm bells start going off. And Isaac's most recent compilation of Midwest erosion rates showed that modern erosion rates in the Midwest are 100 to 1,000 times the natural background rate. And if you assume the natural background rate is the soil replacement rate, alarm bells ought to be going off in terms of planetary sustainability, at least in terms of using soil to grow food. So what I put together in a paper in PNS back when I wrote Dirt was basically this conclusion, that if you take that net loss of about 1 millimeter a year of soil, it implies that you could erode a 0.5 meter to 1 meter thick section of topsoil in about 500 to 1,000 years. And if you look back in the archaeological record, 1,000 years, and again, plus or minus the thick glasses of a geomorphologist looking at archaeology, 1,000 years plus or minus is about the lifespan of most major agricultural civilizations, with a few major exceptions. I hope you're sitting there going, but Dave, what about Egypt? What about the Tigris and Euphrates? What about the Indus and the Brahmaputra? What about the big rivers of lowland China? Well, what is it about all those places where we know farming has been sustained for millennia that is different from a lot of other environments? They're all big river floodplains. And what happens on a big river floodplain? Anybody? It floods, thank you, yes! And what do the floods bring? Stuff. They bring soil, right? They bring dirt, they bring silt, they bring clay, they bring cars, they bring whatever is upstream and it manages to get swept away. But the point being is that big river floodplains, where humanity has managed to sustain farming for millennia, are places where nature can fill the damage from tillage-based agriculture based on natural rates of deposition. That 1 millimeter a year net soil loss off modern agricultural farms, or globally, deposition of a single grain of sand every year could offset that. That's what would happen naturally on a big river floodplain. You start building dams, and you get something like you have today on the Nile River, where with the Aswan High dams that have cut off the sediment supply to the delta, to the Nile, lower Nile and the delta, Egypt has become one of the biggest users of synthetic fertilizers on the planet because they've undermined the natural fertility of their farmland. But the loss of the physical soil itself is not the only thing that's been happening in terms of soil degradation globally. There's also the loss of soil organic matter, which you can think of as the fuel that drives the biogeochemical cycles in the soil that produce the flows of energy and nutrition that keep the plant world and the animal world going. This paper from the Journal of Sustainability from a few years back synthesized losses of soil organic matter in North American agricultural soils and concluded that many farms were at about half the level of when they were first farmed. In other words, we've run down the batteries of our agricultural land by about half, and we've done it in just a couple centuries. What does that actually look like? Well, it looks like this difference. And this time, I'm going to totally turn the lights off for a minute. So hands to yourselves. The soil on the right is a tobacco plantation that is literally a soil from a tobacco plantation literally right across the fence from a forest that has something closer to the native soil. You'll notice the color difference between them. These are developed on the same geology in the same climate, with the only real difference being the vegetation shift in management from converting forest to farming and farming it conventionally for 100 years. The organic matter that colors this soil is basically gone from the conventionally farmed soil. And that is something that is basically characterizes many farms around the world, where organic matter levels are now on average about 2% or less on many of them, whereas if you increase that up to 4%, you could actually radically increase harvests. But that's a longer topic for a different time. So what is it about modern farming techniques that threaten to lose soil and to degrade its fertility? If you look into the processes that degrade soil organic matter in farming, two stand out with a heavy dose of peer-reviewed literature supporting the contention. Heavy routine tillage, like you could find on this sort of pulverized California soil, is a great way to actually reduce soil organic matter. Why? Because tillage oxygenates the soil, it stimulates bacteria that then in turn love to munch on soil organic matter. And so you basically energize the biota without replacing them, and they can consume organic matter fairly rapidly. Now, why is that a short-term advantage to farmers? Because that gives you a burst of fertility. But it also degrades the long-term agricultural potential of the land. So you do it for long enough, often enough, and you can basically turn that dark chocolate soil into the khaki soil that I just showed you. And the overuse of synthetic nitrogen fertilizers does the same thing, but more directly stimulates that bacteria. One of the more interesting research projects I noted in researching this book was how people had used N15 nitrogen isotopes to track nitrogen through agricultural systems, and what they found was that the application of synthetic nitrogen fertilizers didn't dominantly put the nitrogen into the plants, but it stimulated microbes in the soil that consumed that then consumed soil organic matter, which then fertilized the plants. So the very act of adding the synthetic fertilizer was drawing down the native fertility, which, if you think about it for a minute, is an exceptionally clever way to sell fertilizer. May not be the best way to farm. So as I got through writing the dirt book, I was asking myself the question of, well, are we totally screwed? Can we actually reverse these problems and rebuild healthy, fertile soils, and not only on an individual farm level, but on a global level? And if so, how fast could we actually do it? And I'm happy to say that, over the course of 20 years of looking into this, I've become fairly convinced that, yeah, we can, and shockingly fast. This is not an intractable problem, no matter what you might read by idiots in the New York Times these days. And of course, I'm referring to Glenn Greenwald. Do not read his book, it's trash. So basically, what is part of the problem? Conventional agriculture emphasizes chemistry, and there's nothing wrong with chemistry. But what conventional agronomics has left out of the equation is the biology. Regenerative agriculture emphasizes cultivating soil life, and it's the biology in the soils that I've come to see as being incredibly central to driving the processes that make land fertile, and it's also the part that we can fix the fastest. Therein lies the optimistic part. So I'm officially done with the pessimistic part of this talk, so you can breathe a little easier, I guess, about the future of us all until the sun goes supernova, and then we're toast anyway. But I'm going to shift into the second book I wanted to tell you about, The Hidden Half of Nature, because when I finished writing Dirt, Ann and I bought a house in North Seattle, and the process of transforming that yard into a garden really educated us about the role of soil life and drew connections to how we might actually be able to rebuild fertility in degraded soils. What we learned in that book, I've summarized with 3 bullet points here. Symbiotic microbial allies support the health of plants and animals, including people. You've all heard about the microbiome, right? 20 years ago, I don't think I'd ever heard the word microbiome. And in the classes that Ann and I took in soil science, which is the one class we took together in graduate school, we didn't hear anything about microbes in terms of soils and soil development. And it turns out they're really crucial and essential. And you can think of them essentially as trillions of tiny helpers that if we cultivate in farm fields, they can actually assist farmers in building healthy, fertile soils and harvesting high yields from them. But our agricultural strategies and techniques have been working to try and kill them all and degrade them. It's been fairly counterproductive in some ways. How did I get there in thinking about this kind of stuff? Basically, this is the yard at the old house that we had when I finished writing Dirt. Ann wanted a garden on our yard, and you'll notice this beautiful, rich, black earth soil that we uncovered when we pulled that lawn off. Doesn't it remind you of, well, actually it reminds you of beach sand, doesn't it? There wasn't a single worm in that dirt. It was devoid of biology. And Ann, being the biologist, basically realized that we needed to basically try and restore the biology. And so over time, she turned the soil that we started with, this khaki stuff on the left, into this rich black stuff on the right. How does she do that? With organic matter, compost, and mulch, for the most part. But the plants also helped in terms of producing, it turns out, what we come to know as exudates. Now, you've all and it led us to a zone around the roots of plants called the rhizosphere, which is quite literally Greek for zone around the roots of the soil, roots of a plant. And we all know about how plants will take in carbon dioxide from the atmosphere and water up through the roots to put it together to make carbohydrates and build the whole biological foundation for life outside of the oceans. But what I hadn't realized is that there's solid studies that show that plants also drip out of their roots or exude out of their roots compounds that include carbohydrates, fats, and proteins. And they'll exude up to 30, 40, 50% or more of their photosynthate out of their roots. How many of you actually take about 30% of your income and just like every time you get a check, go like throw it on the street somewhere? I've yet to meet some our children. Yeah, children, that's a different thing. That's a sunk cost thing. But why would a self-respecting plant do that? Maybe to feed their seeds. I don't know. But what do we do that is kind of like that? We pay taxes, right? And because we expect to get something in return, like streets that work or a government that's open and functional. Whether that happens or not is another story. But plants exude those compounds out of the roots not because they're just being nice to life in the soil, but they're doing it to recruit microbial allies. They're doing it to feed symbiotic commensal relationships with life in the soil that the plant benefits from. And how does that work? So if you blow up around the tip of a root around the rhizosphere, there's a root coming down here. The plants are releasing their exudates, those carbohydrates, those fats, those proteins, that food into the soil. It doesn't make it very far. It gets consumed within a millimeter to a centimeter of each plant root. And if you want to find some of the most life-dense areas on the planet, go around the roots of a healthy plant and healthy soil. There's a lot of microbial life there. And that microbial life is consuming those exudates, and what does any organism do with something that it consumes? It metabolizes it. What do you do with your metabolites? Well, in this building, we leave them in a special room, but plants basically, or the microbes, release them right around the roots of plants. And what are the kind of things that microbes are metabolizing root exudates into? Things like plant growth promoting hormones. Think about that for a minute. The plants are exuding sugars into the soil to recruit particular microbes that make compounds that make the plant get bigger so it can capture more solar energy and produce more exudates. It's a positive feedback. And those kinds of positive feedbacks and commensal or symbiotic relationships have been instrumental in the evolution of plants, and we've ignored that in agriculture for the most part. Yet it's how nature works. Fungi will extend their hyphae out into the soil and basically grab elements of, say, phosphorus or zinc or copper, mineral elements out of soil particles, bring them back to the plants, and essentially trade them for a cut of those sugary exudates. What kind of micronutrients are they? Well, like iron, zinc, and selenium. We don't need all that much zinc in our diet, but we need a little bit, an awful lot. And you can think about fungi in the soil. They're acting as root extensions for plants that are getting those elements that their own roots can't necessarily reach and getting them into the plants, and that's where it starts to get into the chain that ultimately ends up in us. The other things that plants are making in response to interacting with life in the soil are making things like phytochemicals. Now, what's a phytochemical? Well, phyto is a plant, and chemical is a chemical. They're plant-made chemicals. They're chemicals that plants make in response to environmental stimuli. And there's two sort of styles of environmental stimuli that work for that. One are those commensal relationships, where plants will, in interacting with microbes that are in the soil, they can be then triggered into manufacturing phytochemicals, or they can basically be in response to a stress environment. But what are phytochemicals? Things like the linalool that makes lavender smell the way it does, or sulforaphane that gives the brassicas like broccoli and cauliflower anti-cancer properties when it gets into us, the curcumin that's in turmeric that has similar kind of properties. Now, plants are not making phytochemicals because ultimately when somebody eats them, it may help fight cancer later. They're making them for their own purposes, right? But we've been eating plants for a long time. There's connections in how that all goes through and works. Why are plants making phytochemicals? They're doing it because they serve as a communication means for plants. Think about how plants communicate with one another, not the way we do. They do it through a language of chemistry, and phytochemicals are a key part of chemical signaling that's happening in the soil and actually even in plants. In terms of plant defense, phytochemicals are central to that. There's some examples where when insect herbivores munch on a plant, that plant will send out a chemical signal into the soil to recruit microbes that will come and help stimulate the plant to then produce phytochemicals that repel that particular insect pest. These are highly refined, evolutionarily adapted relationships that are every bit as specialized as what we know between like flowers and pollinators in the world we can see. But this all happens at the microscopic level and out of sight, out of mind. Phytochemicals also will serve as protection. The beta carotene that is in gives the orange color to say squashes this time of year. It's actually an ingredient you'll find in sunscreens. It's great UV protection. What does this all mean? When you start to put this all together, it means that when we think about the soil as a medium for growing food, there's several diets that a soil actually has. So you could translate into a plant diet, if you will. And that is that if we think about soils grown in relatively life-depoperate, degraded soils, we know that we can get high yields by dumping a lot of nitrogen, phosphorus, and potassium on the soil. That's why fertilizer sales are so good these days. We have a lot of degraded land in the world, and we have a lot of people to feed. So we know that you can get high yields in degraded soils, but the plants don't invest as much in their root system. You can test that out, as I have on fields across the Midwest. Go to a conventional farm and try and pull corn stalk up, they'll come right out of the ground. You go to the kind of regenerative farm that I'll describe in a minute, try and pull them out of the ground, doesn't work. They have bigger root systems. So soil that's plants that are grown in organic matter-rich, healthy, fertile soil will invest more in their roots. Why? Because they're getting a bigger return in terms of micronutrients and beneficial microbial metabolites from the life that's in the soil. As you might imagine, if you're getting less in terms of a degraded soil, you might imagine that the plant health might suffer. Its defensive systems may be compromised by the reduction in soil organic matter and soil life in the soil. And that's essentially what has happened. I don't think it's any coincidence why global sales of pesticides went through the roof after global sales of fertilizers. And one of the little-known bits of agronomic trivia I've picked up along the way is, guess which kind of farms tend to have more insect pests? Organic farms that don't use synthetic pesticides or conventional farms that use synthetic pesticides? There's a very clear answer in the peer-reviewed literature. Who votes for the conventional farms? Yeah, the conventional farms are the ones that have the more pests. The ones that use, the more pesticides we use, the more agricultural pests we have on our farms. I defy you to find a pesticide company that advertises that relationship. But it's all over the peer-reviewed literature. So basically, when Ann and I finished writing The Hidden Half of Nature together, we were left with question. We were convinced that the key to rebuilding fertile soils lies in the biology. Why? Because how long will it take you to take a hunk of granite and turn it into a soil? You go take a hunk of granite, leave it out in the city street somewhere. Your grandchildren could come back, and it'll still be a hunk of granite, right? You can add the life back to soils. If you have the mineral part, you can add the life back really fast. That's what Ann did in our yard. We didn't truck in any of the mineral part. We had that already. She brought the biology back to life. So we were left with the question of, well, could you do this on a real farm? It's one thing to do it in a residential setting in Seattle where we have access to zoo, dew, and coffee grounds and all kinds of sources of organic matter. But the next book that I worked on is called Growing Revolution, where I basically went to farms around the world who had already done to their farm what Ann did to our yard, and I asked the question of, what did you do? And then tried to draw parallels between what people in equatorial Africa, Central America, and all across North America, from small-scale vegetable farms to huge mechanized farms, did. And what I basically found is that regenerative farming can restore soil fertility remarkably fast, and by remarkably fast, I mean like in a decade or two or less. And to me, that's remarkably fast. And that farming and ranching could put a lot of carbon back in the ground. I'm not going to offer you a number, because I could give you ranges from 5% of offset of current fossil fuel emissions to 100%, and neither end of that's credible. The answer is somewhere in the middle, and people are going to argue about that for some time. But what I do think is relatively inarguable is that there's a simple recipe for accelerating the increase in soil organic matter, or carbon in the soil, that boils down to the commonalities in all the farms that I visited around the world that had done it successfully. And that involves minimal disturbance, so that's not tilling, ditching the plow. It involves always keeping the soil covered, so planting cover crops between one's cash crop, and planting diverse crop rotations, not just planting, say, corn and soybeans, but having at least 5 or 6 plants in a rotation. Now, and some of these regenerative farmers were reintegrating animal husbandry by allowing cattle to graze off their cover crops or their main crops. And what is it about this combination of practices that would work to rebuild life in the soil? Well, providing a stable place to live, feeding them, and giving them neighbors to partner with. It's basic ecology. And yet, this is the exact opposite of what we've been teaching people how to farm for 100 years, where we've been teaching them to use tillage-intensive things that leave the ground bare in between crops and to concentrate on either monocultures or functional monocultures like a corn-soybean rotation. In other words, we've been kind of on the wrong track in thinking about the soil and soil life in agriculture. How fast can reversing that thinking and putting it into action actually work? This gives you an example from David Brandt's farm in Carroll, Ohio, where you'll notice that this is the soil that he started with in 1971. It looks a lot like that khaki tobacco plantation that I told you about. This is the soil he had in 2014, the year before I visited him. It looks like rich black chocolate earth. This soil, he basically, well, I'll show you what he did in a moment, but he basically, in a couple decades of farming, he took completely degraded land, rebuilt the fertility of his soil, all doing it while out producing his conventional neighbors, and he did it quite profitably. And he did it by following those kinds of practices I was just telling you about. This is David here modeling his tillage radishes. There's about 12 different cover crops growing in this field behind him. His neighbor's sickly soybeans are behind. And what he did is he walked me through the economics of his farm, which is what started to turn me into an optimist that this kind of style of farming, this regenerative style of farming that can rebuild fertility, might actually get adopted more widely. Why? Because it can make farmers more money. So David's neighbors are doing full tillage at adding 200 pounds of nitrogen per acre and 2.5 quarts of Roundup. In 2015, the year I visited, the neighbors were on average spending $500 an acre to harvest 100 bushels. That at $4 a bushel, what they were getting, then they were losing $100 an acre. The more they worked, the more money they lost. That sounds like grad school, doesn't it? What David Brandt was doing was he'd been doing no-till for about 44 years. He had then moved into doing cover crops. And by the time I visited him, he was not tilling at all. He was using 1/8 of the nitrogen and about roughly a third, just maybe a quarter to a third of the Roundup. He's not an organic farmer. In fact, he would have punched me if I called him an organic farmer. So I teased him and said he's organic-ish, because he basically has weaned himself, and before he died a couple years ago, he got himself completely off of agrochemicals. No fertilizers, no pesticides. How did he do it? Well, no-till, cover crops, and diversity. And he got most of his diversity in his cover crops, because he sold wheat, corn, and soybeans. He only had 3 cash crops, but he grew a lot of different cover crops. What was he doing? It cost him $320 an acre. He was harvesting not quite twice what his conventional neighbors were. This is not an issue of feeding the world versus environmentally friendly farming. That's one of the biggest myths out there in agriculture. He was outproducing his conventional neighbors, and he was making $400 an acre when they were losing $100 an acre. If we really wanted to have a progressive agricultural policy in this country, we ought to be able to sell it to farmers as a way to actually solidify their bottom line. The people who are making money in agriculture today are all the middlemen. The people selling farmers the things they think they need to farm productively. This gentleman here is named Kofi Boa. He's one of the farmers I visited in Africa. He runs the No-Till Research Center in Kumasi, Ghana. He worked in a region that has done the traditionally slash and burn style of agriculture, which worked great until their population got large enough that they were slashing and burning the same fields every year and not moving it around because their forest was, the remaining forest was in preserves and not to be farmed. And at that point, if you continue slashing and burning the same bit of land over and over, you degrade it. What Kofi did is he taught the people in his village how to basically go to no-till with cover crops and a great diversity of cover crops. The same 3 regenerative principles. It shut erosion off. The traditional style of erosion was something like 20 times faster than the no-till erosion, so it's helped solve the erosion problem. But what I want to focus on here are the yields. Notice that the traditional yield of corn tripled under the no-till system, and the cowpea yield doubled. This radically transformed the economics of his village to the point where they became much more prosperous than they had been using traditional methods. So the idea of regenerative farming as simply a return to traditional farming is not true. What we're really talking about is trying to take the ancient wisdom of things like cover crops and crop rotations, which are not new ideas, but combining that with modern technology that allows us to do no-till and to do it with a different style of farming. The last farmer I'll show you is Gabe Brown. He runs Brown's Ranch, which he likes to advertise as regenerative agriculture. The reason I'm showing it to you is that he's reintegrated animal husbandry into his cropping operation. And you hear a lot in the literature these days about how animal agriculture is bad for the planet and bad for people. There's a caveat, though. It matters how you do it. If you do it the way that Gabe's doing it, you can actually restore your land and grow better food. What he's doing is he's basically taking the livestock in to graze off the cover crops in his market garden. He brings the chickens in to eat the flies that come along with the cow pies. And what that has done is it has accelerated the cycling of carbon and organic matter back into his soil. This is the soil on that field that I just showed you. It has about, I think it's about 8% organic matter. His neighbor's organic farm has about 2 to 3% organic matter. This is not a question of organic versus other styles of farming. It's about how you treat the soil in any kind of farming system. And this shows you data on topsoil depth and the organic matter content of Gabe's soils as he transitioned from starting no-till back in 1993 when he started with 3 inches of topsoil, and that is basically the depth that you can identify as topsoil, so it's the O and A horizons. And he started off with about 2% organic matter. He then diversified his cash crops, he integrated cover crops, he then got to multi-species cover crops, and then he brought the cows in. And by the time he'd done all this, he'd tripled his organic matter. And we've actually measured this in a study that Ann and I did that I'll show you in a minute that confirmed his reporting of this. Tripled his organic matter. And he took his soil depth, topsoil depth, from 3 inches to 14 inches. So he not only tripled the concentration of organic matter, he quadrupled the depth of it. You put those two things together, and he raised his organic matter content by an order of magnitude. And he did it in a couple decades with intensive farming practices. That is so counter-narrative in the agronomic world that I can't begin to describe that to you. I had to write a book about it. But it turns out that same kind of thing was happening on the UW campus the entire time I've been teaching here. I did not expect that. I had this wonderful student, Julia McRae, who some of you may remember, who came through the department a few years back and did a senior thesis with me looking at the UW Student Farm. If you haven't been over to the UW Student Farm, it's over by, if you go past the IMA down towards the Center for Urban Horticulture, it's down there. They have a bunch of different beds in the farm that have been farmed for different periods of time using these same regenerative techniques of minimal tillage, diversity, and cover crops. And what you can see, if you basically take that, if you do the space for time substitution and you look at what the soil organic matter content was in the beds of that farm under different years of management, so ones that have never been managed, so it's like they were at the start, or ones that have been managed, the first ones that they did, there's a weak but positive relationship. And the thing that I emphasize is that the stuff in here, there's a lot of year-to-year variability because they use a lot of compost and mulch. And when you throw a bunch of compost and mulch on the field, the organic matter content goes up, and then it goes down for a couple years, and it goes up. So it's highly variable. But notice that at the start, it was down here 5 or less, 15% over there. It's a roughly doubling or tripling of the organic matter content in 20 years. That's what Gabe Brown did on his farm. And the UW student farm kind of did something similar, especially when you look at the topsoil thickness, where it started out being a few centimeters, and it's gotten up to 20 centimeters. That thickness has quadrupled in 20 years. It's a big change in organic matter. And if you run the numbers, and you're willing to accept the polite fiction that you could do this same thing on all farmland around the world, which you can't, but if you accepted that fiction, and I've never published this analysis because I don't believe it, but you could virtually offset fossil fuel emissions. Now, I don't think you can get that much soil into that much carbon to that many soils that fast around the world, but the point is that you could put a lot in, and that there's no downside to doing it because we can harvest comparable amounts, and we can do it for less. And you don't necessarily have to take my word for that. I compiled a number of anecdotes in the Growing Revolution book, but Claire Lacan and Jonathan Lundgren published a paper, I think the year after the book came out, that basically looked at comparing the revenue and cost for conventional and regenerative corn in the Corn Belt of the U.S. And I think there's about 20 farms each averaged in these two bar graphs. But the way you read it is the top is how much the farmers harvested off the fields, and then the colored things are all the things they spent money on, which means that the white bit at the bottom is what's left over as profit. And what I want to point out are two things. First of all, the regenerative fields harvested more. Again, this isn't about feeding the world versus a better style of environmentally friendly farming. We can have our cake and eat it too in this case. But notice that the profit for the regenerative farms was a lot higher because they spent a whole lot less to grow more. That's a winning recipe. It took me about 4 years of talking at farming conferences around the Midwest, because I got a lot of invitations to do that after I wrote Dirt. About 4 years to realize that it was not the right way to start off saying, you could put carbon in your soil to offset the climate problem. Now, I almost got run out of town a few times saying that. Instead, if you go and say, I can cut your fertilizer bill in half or more, everybody goes like, how? There's a way to approach it. So thinking about benefits of healthy soil based on what I've shown you so far, I put higher farmer profits at the top, because if you're going to actually have any style of farming be sustainable, it has to sustain the farm. It's got to work for the people. And it also, you can produce comparable yields, but there is a transition. You can't just flip the switch the way Sri Lanka tried to do a few years ago and go organic overnight. That's a recipe for idiotic disaster. It's kind of like if you're an alcoholic and you just quit drinking one day, you're going to feel like shit for a while. You can less fertilizer, pesticide, and fossil fuel use. You're not recording this, are you? Using less fertilizer, less pesticide, and fossil fuel is the reason why you can basically have a more profitable farm with comparable yields. But it also benefits society at large off the farm in terms of carbon sequestration, water retention, which translates into drought resilience on farms, and less off-site pollution. The single best way to reduce nitrate and phosphate pollution in, say, the Gulf of Mexico is to reduce the amount that we use on farms in the Midwest of North America. It's really pretty simple. The last bit I want to talk about is really what I promised to talk about, which is the most recent book, What Your Food Ate. This is one that Ann and I wrote together that tries to deal with the connection of soil health and human health. Because by the time I got through writing Growing Revolution, I was convinced that farmers could restore fertility to their land. But there was an open question as to what do these regenerative practices that cultivate the beneficial life in the soil do to what actually gets into our food and therefore into our bodies, and does that matter? Because if there's one thing that people care more about than the soil, okay, there's a lot of things people care about more than the soil, but if there's one thing that I'm certain of, it's their own health. What Ann and I found, basically, and this was literally our pandemic project, if I recall right. It was published in 2022, and we spent 2020 and 2021 just hiding and writing this book. We basically scoured the literature for everything we could find on how farming practices affected what's in food. And if you're really interested in the content behind this, we published the document that has all our sources. There were literally 1,000 sources we consulted for it. We basically found that farming practices affect levels of phytochemicals that we talked about earlier, and vitamins and minerals. That's the life in the soil, basically collaborating with plants to get those into foods, but also the omega-3 and 6 fats in meat and dairy products. It turns out that you really should prefer that grass-fed meat and dairy to the corn-fed meat and dairy based on the fat profile of it. If you're really curious, read the book. We won't weigh into that. I'm not going to go into that today. And microbial metabolites. That's sort of like the black box of nutrition in thinking about the way that Ann and I hadn't been exposed to the microbes in the rhizosphere when we were trained in thinking about soil science. Nutritionists today are really starting to grapple with realizing that how the way that microbes metabolize what's in our food turns out to be really important to what it does for our health. And the importance of that will become clear in a minute. I've just got a couple more slides. So one of the things, Ann, I did realize in trying to get into this does soil health affect human health connection is that there's an awful lot of dots and disciplines between those two things. You've got to think about how do farming practices affect the soil and soil health, how that affects crop health, how that affects livestock health, and how that all integrates up to affect human health. And it's very difficult to experiment on entire populations in this way. Like, where does your food come from? Do you have any idea? You go into whatever place you buy your food, the only place you're going to know is if you go to the farmer's market and you interrogate them about, is this from your farm and how did you actually farm? The only labels we have are organic and conventional, and we go into the book why that's inadequate for looking at characterizing what's in food. So we decided we had to run a pilot study ourselves to look at how regenerative farming could affect the nutrient density or what's in foods. So we picked 10 farms across the country where we paired a regenerative farm and a conventional farm, literally sort of across the fence row comparison. We tested their soil health, their organic matter, and their soil health score from the Haney test for those of you who are into agronomy. And we also tested the nutrient density of crops that the farmers grew in those fields in the same year side by side, and then we looked at the ratios between them. Why did we look at the ratios? Well, imagine the diversity of geology that we have in terms of our sampling things. We're looking at relative effects on all these together. And what we basically found is that in terms of soil organic matter, the regenerative farms had on average about twice the soil organic matter, similar to what we were seeing that someone like Gabe Brown had done to his farm. In terms of soil health scores, it was 3 times higher. So we were basically confirming that these regenerative farms had increased their organic matter and their soil health, and we defined the regenerative farms as farms that had used these regenerative practices of minimal disturbance, cover crops, and diversity for between 5 and 10 years. That was our window. And the conventional farms, they were using county average methods and techniques. We then had the farmers grow various crops in the adjacent fields, and on average, in terms of important classes of phytochemicals, the regenerative farms had about 20% more. In terms of vitamins, 15 to 30% more on certain vitamins. Those are numbers that are big enough to actually start going, hey, there may be something here. And now there's a master's student in public health who's been working out at the UW Student Farm who's managed to confirm that gradients in soil health between otherwise identical beds that have just been farmed regeneratively for different periods of time have up to 3 times different levels of certain phytochemicals in them. So there's a very real effect of soil health on what's in our food. Why does that matter? Well, the phytochemicals not only serve the purposes of communication and protection and defense in plants, they do it in our bodies too. That's part of what the whole gut microbiome thing is all about. But it turns out that those phytochemicals that are in plants that are enhanced by regenerative farming and degraded by conventional farming actually serve as the feedstock for for production of medicinally beneficial compounds that get processed right inside our bodies. What are the sources of phytochemicals? Fruits and vegetables are the best sources of them. Meat and dairy that was actually grass-grazed is another actually good source of them, where it can have up to 20 times higher phytochemical levels than in feedlot-raised and corn-raised meat and dairy. But so when we eat foods that have phytochemicals in them, they go down the hatch, and the human microbiome engages with them in our colon. And what happens there is a bit of biogeochemical alchemy, in which the human microbiome metabolizes those phytochemicals that are packaged up with food particles, or in food particles, and turns them into compounds that the peer-reviewed literature has basically documented can have anti-cancer, anti-diabetic, anti-inflammation, brain health supporting, cardiac support helping effects. There's a big medical literature on what these compounds actually do. Collectively serves as a pretty damning indictment of how we've been going about growing our food on this planet. If you think about it in terms of planetary management, in terms of sustainability of large populations of people, and if you add the caveat of healthy people, it's even more interesting. I will I just sent off to the publisher literally last week. It'll be out next summer, and it takes the science behind everything I've been talking about today and tries to put it into one relatively short book. Because what I've been amazed by is how much peer-reviewed science has come out in the last few years as we've been writing these books that just supports everything I've just been telling you. Any of you who are interested in a seminar in the spring, I'm doing a 490 seminar on the 3 books I didn't talk about today. It's a wonderful seminar format, mostly discussion. It's my favorite class to teach. Invite anybody who's looking for a class spring quarter to take it. And finally, if you're looking for something to do on a weeknight, feel free to come out and see my band, Big Dirt. We're playing at the Sunset November 30th, and you've got lots of other chances to see us. So anyway, happy to take either questions here or at liquefaction. Those of you who are not in the department, don't miss liquefaction. I think it's otherwise known as free beer, if I'm not mistaken. Yeah, if we have time, I'll be happy to take questions.
All right, thank you, Dave. So we have some time for questions. I'm going to give you the microphone because I think your lapel has died. And so, but please shout out your question.
Yeah, Baptiste. The biggest farm I've been on that I am certain would count as regenerative, because I've dug holes in it and holes in the neighboring farms, is 20,000 acres. It's as big as they get. So what I've actually become convinced by is that the scaling argument is more about technique, and the idea of minimizing disturbance is one. It's sort of the next level up. It's a philosophical level of how we're thinking about the soil, and then how you would actually devise a system to do minimal disturbance on huge land. So how did they do it on this 20,000 acre farm? It was all mechanized, so it was a totally industrialized farming. And so I think it's wrong to think about industrialization of farming as being inevitably bad. Unless we all want to be farmers, at some level we have to do that. So it's all about how we do it. And so what they did is they got John Deere no-till seed drills. So they were not plowing, they were planting through they would just like knock over last year's crop and plant right through it. And they were planting cover crops, a great diversity of cover crops in between their cash crops. And, over the course of 5 or 10 years, it worked like magic on their soil. Now, there's definitely a transition period. And like the yields, it takes like at least 3 years to get yields back to the conventional level. It's not like you can flip a switch and do it overnight. You've got to rebuild the biology and the organic matter to actually get that productivity. But in the big scheme of things, 3 years is not a big deal. The problem is 1 year is a big deal to a farmer, right? Because I had not realized the magnitude of economic over-leveraging most farmers do. They'll borrow like $800,000 a year to make 80K. I would never do that. It's insane. But they do it year after year. So one of the big policy tricks to speed adoption of this would be to figure out how to reduce the marginal risk exposure of farmers going into it. And that's all about how we structure crop subsidies and crop insurance, and that's in the policy world. And Eric, you had a question. Yeah. 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 Sure, let's do that. Yeah, I do. When I wrote Dirt, and Dirt came out in 2007, so we're approaching 20 years on it. I would go speak at farming conferences, and nobody was talking about the concept of soil health. And in that book, I basically argued we needed to build soil health as the future of farming. Now you go to any soil conference anywhere in the world, it's what they're focused on.
And I think the reason is because the economics is starting to line up so that it makes sense to actually try and use essentially ecological processes, the productivity of trillions of microbes to actually do what instead they had been paying a company to come in and spray on their fields. So I've seen in terms of no-till, something about a third of U.S. cropland is no-till now. South America is way ahead of us. They're like 80, 90%. Europe is behind us, but in terms of cover crops, Europe's been pretty good. There's been, I've had a lot of interest from China in terms of rethinking agricultural practices, and two of the books have come out in Chinese editions recently. So there's a lot of interest, but there's a long way to go. If you look at how many farms in the U.S. are actually adopting all three principles, it's probably around 3%. It's kind of like it's a little bigger than organic, but not much. And there's great arguments between the regenerative and organic camps about who's right. And it's like, you're both right. Just keep doing it. So yeah, I think there is momentum, but that momentum is not being watered in the policy arena. And so with every farmer I talked to on 3 continents basically said that if they were getting subsidies based on the organic matter content of their soil, they would do more to increase it. So I think you're absolutely right about incentives, and I think we have them on backwards. And we have for 100 years. Nicole, you had a question. Thank you. Oh boy. Well, there's several levels to that. The first one is I would encourage most people to just become more aware of where your food comes from, because that is affecting what's getting into you. And some of the narratives we hear about what to eat really ought to be predicated on how it's grown. And so there's a lot of people who try and vote for the environment with how they spend their food dollars, and it's not clear to me that they're all spending it in ways that are consistent with their values and goals. So the first thing I would do is say, people ought to become more aware of where that's coming from and how that lines up. And then also political pressure. We weren't going to talk about the political moment, so I'll talk about it in the abstract. When consumers in the states that are not major agricultural producers start getting concerned about what's in their food and having their representatives care about the farm bill, that's when you're going to see major league change in terms of the incentive structures. So I'd encourage. So I've talked to Representative Kim Schreier, who's a wonderful representative locally, who's both a pediatrician, but she also gets the farming thing. She's got a lot of farmers in her districts. It's people like her that need to basically carry the banner forward in the legislative area. But so awareness and pushing are probably the big things. It is frustrating, but you look at the magnitude of the impact of our food system globally. Our individual impacts on it are small, but collectively they're huge. So how you separate that or parse it, I'm not exactly sure, other than that what each of us does matters. Yeah. So the question is, could these techniques work in arid areas like the Southwest? And that is a super good question that I'm not entirely sure the answer of, because I haven't done much work in those areas. Where I can say, where I would see that would be in terms of regenerative grazing practices, which is a whole thing I didn't really talk about today, but it's very parallel. There's a different set of strategies that can be used for that do work in semi-arid grasslands really well. But one of the things I'm curious about, I think, is if you look at sort of the way we use different sort of biomes around the world, a lot of those semi-arid grasslands that could be restored by grazing, and I'm thinking like the Sonoran Desert and the Sahel in particular, places I've seen examples that have worked. Those examples are, I'm sorry, how to put it, that could actually work fairly well. in areas where sustained cropping based on groundwater discharge may not be actually sustainable. And so I sort of wonder how much some of those regions are better suited long-term for grazing than cropping. But it's going to depend on the local conditions too. But I mean, the challenge in arid areas is it's really hard to keep organic matter in the soil, and there's not much to begin with. So I'll give you a definite, great question. I'm not entirely sure of the answer. David, you get the last question. Mm-hmm. Mm-hmm. Yeah, and that lasted until the 1950s. Oh, there. Basically, if you read the USDA's Yearbook for Agriculture, and I think 1933, and I might be off by 1 year or so, there's a whole section on cover crops and crop rotations and how they enhance crop yields. They were onto that. Now, they didn't get to the no-tilling part until much later, and there's big arguments about tillage in the 50s and 60s. But the basic ideas of cover crops and diversity and rotations, they're old ideas. And they've characterized a lot of traditional styles of agriculture, but it's coupling it with the minimal physical disturbance that is really sort of novel and new. And a lot of what happened to the USDA programs is that they were actually quite effective at reducing soil erosion, down to only about 3 or 4 times what the natural replacement rate was. So they knocked a big chunk of it off, but they didn't solve the problem. And then in the 1950s, there were major changes in agronomic policies that completely sort of changed the widespread adoption of that culminated in, Earl Butz in the 70s going, get bigger, get out, just like plow everything and sell it to the Russians because they're starving and we want their money. There's a lot of very interesting policy things that I have not written that much about because that's really not. I mean, it's the part that probably is the most important, but I don't find it the most interesting. I mean, I would basically go do what Eric was suggesting: set the incentives up so that people want to do this, and then they'll do it. And we've managed to set it entirely backwards because we had the idea in the 50s that efficiency on farms meant separating animal husbandry from cropping, and using a whole lot of synthetic fertilizers to grow high yields of crops on degraded land. And one of the big reasons that nitrogen fertilizers took off in the 30s is that we'd already degraded soil organic matter a lot. That's stuff I wrote about in Dirt. But it worked to boost yields, and so then the challenge was, what do you do with all that cheap corn we've been growing? Well, you feed it to cows. And that cuts cows out of the cows are no longer manuring the fields. There's a whole series of changes that swept through agriculture that got us to where we are today. And I mean, what I've been arguing about since I wrote a piece in Nature, I think in 2010, that we needed to basically, we basically need another agricultural revolution based on prioritizing soil health to rethink all the practices and policies that flow from the philosophy that we actually look at it with. So that's what I tend to get in trouble for today, is arguing that we need to think about farming differently, because once you think about it differently, people might act about it differently. But my habit is to go to the peer-reviewed literature to figure out, is the argument I'm making actually going to make sense? What's the lithologic diversity of Mars? I mean, it's like, I don't think basalt has everything we need. But yeah, yeah. But what I would, probably the first thing I'd recommend is you'll want to bring a whole
like sourdough starter. I'd bring a little bit of heavily impregnated with microbes soil that you sort of foster along the way, but a starter set. Yeah, because there's no way you're going